Is it a dirty cosmic snowball made of ice and dust and rock and gas? Is it a natural comet, or is it something else?
New images of 3I Atlas were expected to bring clarity, yet instead they pushed scientists into deeper uncertainty, because the moment this object passed the sun should have stripped away illusions and revealed its true nature. If 3I Atlas is a comet, then it behaves unlike any comet ever recorded, but if it is not, we may be watching something entirely new moving through our solar system. What stands out is not fear, but confusion, since every frame adds detail while removing certainty. Rather than answers, the images created layers of doubt, forcing experts to pause and rethink what they see. So if the pictures raised more questions than solutions, what exactly did they fail to explain? The story of 3I Atlas began in July 2025 when a routine scan quietly picked up something that did not behave like anything astronomers were used to seeing. The Atlas Survey telescope in Chile was doing what it always does, scanning the sky night after night, tracking faint points of light that usually turn out to be ordinary asteroids or distant comets. This time, one signal refused to fit the pattern because it was moving far faster than expected and cutting across the sky at an angle that felt wrong. At first, the object appeared as a weak blur, barely standing out from the background of stars, yet its motion immediately raised concern. Most known objects shift slowly between images, but this one jumped forward with unusual speed, forcing automated systems to flag it for closer inspection. When researchers checked the data, the numbers did not settle their nerves since the velocity was far beyond what is typical for objects born inside the solar system. What made the moment unsettling was not just speed, but unfamiliarity. Astronomers rely on patterns because planets, asteroids, and comets tend to follow rules that repeat over decades of observation. This object refused to follow those rules, and the early calculations suggested that it was not circling the sun in a stable loop like most visitors we know. Instead, it looked as if it was passing through, as though it had arrived from somewhere else and had no intention of staying. In the hours that followed, teams began sharing measurements and refining the trajectory, hoping the strange behavior would fade with better data. It did not. Each update only reinforced the sense that something about this discovery was different because the path remained steep, fast, and difficult to reconcile with familiar models. Even before names or classifications were discussed, the unease was already there, growing quietly behind computer screens. The object did not arrive with drama or spectacle, yet its silence made it more unsettling. There were no sudden flashes or bright tails at first glance, only a faint mark that kept outrunning expectations. That subtle entrance mattered because it meant the discovery was driven by data, not by imagination or hype. Scientists were not reacting to a rumor, but to numbers that refused to behave. This moment became the foundation of everything that followed. Before debates about composition or origin, there was a simple realization shared across observatories, which was that this object did not resemble anything comfortably familiar. It was the point where curiosity turned into sustained attention and where routine observation shifted into focused investigation. If the first signal already challenged what astronomers expected to see, the next question was unavoidable. What exactly was this object that refused to move like the rest? At the center of the early confusion was how 3I Atlas appeared in its first images, because what astronomers saw did not resemble a typical space object at all. Instead of a sharp point or a clear streak, the object showed a bright core wrapped in a soft, hazy shell, creating a shape that many described as organic rather than mechanical or rocky. To the human eye, it looked less like a comet and more like a microscopic cell floating in darkness, with a glowing center and a blurred outer layer. This impression mattered because visual data often shapes first conclusions. Astronomers are trained to read patterns in light, yet even experts can be misled when an object is distant, fast, and partially hidden by glare. In these early frames, sunlight scattered through gas and dust created a smooth halo, while the central brightness appeared compact and stable. That combination gave the illusion of a self-contained form, as if the object had structure rather than motion. The confusion began to clear only when scientists compared images taken from different angles and at different times. When the object shifted relative to the sun, the glowing shell stretched and changed shape, revealing that the haze was not a surface but material being pushed outward. What had looked like a surrounding membrane was instead a cloud of gas and dust, and the bright center was not a solid shell but a nucleus buried deep inside that cloud. This shift in perspective changed everything. The glow was no longer mysterious light, but a coma, which is the familiar envelope that forms when ice heats up and releases gas. The faint extension trailing away from the sun began to stand out more clearly, confirming that the object was shedding material rather than holding it together. In simple terms, the cell-like appearance was not a sign of life or design, but the result of physics, distance, and angle working together to fool the eye. Even so, the early illusion left a lasting impact. It highlighted how easily the brain searches for meaning when faced with something unfamiliar, especially when details are limited. In space observation, images rarely arrive as clean portraits because they are shaped by light, motion, and the limits of our instruments. 3i Atlas became a reminder that seeing is not the same as understanding, and that first impressions can point in the wrong direction. This stage of identification was not about labeling the object yet, but about stripping away assumptions. By recognizing how the visual trick occurred, scientists could move forward with a clearer framework for analysis. The object was not behaving strangely because it was alive or artificial, but because its environment and motion created a misleading picture. Once the illusion faded, a more grounded question took its place. If the strange shape could be explained by light and dust, what deeper evidence was needed to decide what this object truly was? The turning point in the story came when scientists moved beyond first impressions and focused on measurable evidence, because classification in astronomy depends on data rather than appearance. As more observations came in, the behavior of 3i Atlas began to match patterns that researchers recognized, even if those patterns appeared in an unusual form. The key was not how strange the object looked, but how it reacted as it traveled closer to the sun. One of the strongest signs was the presence of an icy nucleus, which is the frozen core that defines a comet. As sunlight reached this nucleus, heat caused the ice to release gas, and that gas formed a glowing cloud around the center. This cloud, known as a coma, is a classic feature seen around comets throughout the solar system. In the case of 3i Atlas, the coma was faint at first, but it became more defined as observations improved, confirming that the object was actively shedding material rather than remaining solid and unchanged. Another important clue came from the way the surrounding dust behaved. Particles released from the object did not scatter randomly, but followed a direction shaped by solar radiation. This pattern suggested that pressure from sunlight was pushing material outward, a process that fits well with comet physics. Asteroids, by contrast, tend to remain relatively stable and do not produce large clouds of gas and dust when warmed. NASA's conclusion was not based on a single image or measurement. It came from a growing collection of consistent signals that pointed to the same explanation. The object showed a nucleus, it developed a coma, and it responded to solar heat in ways that matched known comet behavior. Taken together, these signs formed a clear picture, even if some details remained unclear. Yet this confirmation did not close the case. While NASA classified 3I Atlas as a comet, it quickly became clear that this was not a typical example. Most comets belong to the solar system and follow long repeating paths shaped by gravity over millions of years. This one did not. Its trajectory hinted at a much deeper mystery, because nothing about its motion suggested it had formed alongside the Sun. The confirmation therefore solved one problem while creating another. Scientists could now say with confidence what kind of object they were observing, but they could not explain where it came from. The label of the comet described its structure and behavior, yet it said nothing about its origin or history. In that sense, the word clarified the present while leaving the past completely open. This moment marked a shift in the investigation. The question was no longer whether 3I Atlas fit into a known category, but whether that category was enough to explain its journey. If it behaved like a comet but did not belong to the solar system, then the next step was unavoidable. How could a comet with familiar features arrive from a place far beyond the Sun's reach? The strongest clue that 3I Atlas did not belong to our solar system came from its path, because motion tells a deeper story than appearance ever could. Most comets follow long, looping routes shaped by the Sun's gravity, returning again and again over thousands or even millions of years. 3I Atlas did not behave that way, since its trajectory showed no sign of turning back, as if it had no bond with the Sun at all. When astronomers traced its orbit, they noticed something unsettling. Instead of curving into a familiar ellipse, the object cut through the inner solar system on a steep, open path. This type of motion means the Sun's gravity was not strong enough to capture it, which immediately suggested an origin far outside the planetary family we know. In simple terms, 3I Atlas was not visiting on a schedule because it was never meant to stay. Speed added weight to that conclusion. At the time of its discovery, the object was traveling at roughly 137,000 miles per hour, a pace far greater than what is typical for comets born near the Sun. That kind of velocity is not easily explained by local gravitational nudges. It fits far better with the idea of an object that spent millions of years drifting through interstellar space before briefly crossing our neighborhood. This realization placed 3I Atlas into a very exclusive category. In the entire history of modern astronomy, only two other interstellar visitors had been confirmed before it. The first was Oumuamua, which stunned scientists with its strange shape and lack of a clear tail. The second was Borisov, a more familiar comet that still carried the unmistakable signature of an outsider. 3I Atlas became the third, and its arrival reinforced the idea that these encounters, while rare, are not impossible. What made this discovery feel different was its timing and clarity. Unlike earlier cases, astronomers detected 3I Atlas early enough to track its motion with precision as it moved deeper into the solar system. Each update refined the same conclusion, which was that this object was on a one-way journey. After passing the Sun, it would continue outward and eventually vanish back into the vast space between stars. There is something quietly humbling about that path. 3I Atlas likely formed around another star long before our Sun even existed, then wandered the galaxy for billions of years without purpose or destination. For a short moment, it crossed paths with Earth, offering a rare chance to study material shaped by a completely different environment. Soon, that opportunity would be gone forever. This understanding shifted the tone of the investigation. The question was no longer whether 3I Atlas was unusual, because that much was clear. The real challenge became how much information could be gathered before it disappeared from view. If this visitor truly came from another star system, what new details might its next close encounter reveal? The investigation entered a new phase when 3I Atlas passed close enough to Mars to be seen from a completely different vantage point, because observing an object from multiple locations can reveal details that Earth-based telescopes often miss. Spacecraft operated by the European Space Agency and NASA were already active around the Red Planet, and for the first time, their instruments captured images of an interstellar visitor moving through the inner solar system. This shift in perspective mattered, since it allowed scientists to see how the object behaved in real time as it interacted with sunlight and space itself. Among the most striking findings was a faint but expansive cloud of hydrogen surrounding 3I Atlas. Hydrogen is the simplest and most common element in the universe, yet seeing it spread so widely around a moving object raised immediate questions. This cloud suggested that water or other hydrogen-rich compounds were breaking apart under solar radiation, releasing atoms that drifted far beyond the visible coma. In simple terms, the comet was not just glowing, but actively losing material in ways that extended far beyond what the eye could normally detect. These observations added a new layer to the puzzle. From Earth, much of this hydrogen cloud would have been invisible, masked by distance and brightness limits. Near Mars, however, sensitive instruments could trace its shape and reach, revealing how energetic the interaction with sunlight truly was. The data showed that the cloud stretched for millions of kilometers, turning the space around the object into a vast, invisible envelope. What made this especially important was timing. Interstellar visitors do not slow down or wait to be studied, and 3I Atlas was racing through the solar system on a narrow window of opportunity. Every hour mattered, because conditions near the Sun change rapidly, and the processes releasing gas can weaken or disappear as distance increases. The Mars-based images captured a moment that would never repeat, freezing a brief stage of activity that could soon fade. Scientists also noted how the hydrogen cloud aligned with the object's motion. Its shape hinted at how radiation pressure and solar wind were shaping the released atoms, offering clues about the comet's composition and structure. While these details did not answer every question, they provided valuable constraints, narrowing the range of possibilities and ruling out simpler explanations. The broader meaning of these observations goes beyond one comet. They demonstrated that planetary spacecraft can act as remote observatories, extending human vision deeper into space. For planetary defense and future research, this approach represents a major step forward, since it allows tracking and analysis from multiple angles rather than relying on Earth alone. Yet with every new image came a familiar feeling. Instead of settling the mystery, the added detail highlighted how much remained unknown. The hydrogen cloud explained activity, but not origin, and it described behavior without revealing history. As the data continued to arrive, one question naturally rose above the rest. If these new observations showed what 3I Atlas was doing, could they also help explain why it behaves so differently from everything we know? The deeper scientists looked at 3I Atlas, the more three anomalies began to stand out, because each one challenged expectations in a different way while still pointing toward a single unsettling picture. None of these features alone would be enough to rewrite what we know, yet together they formed a pattern that refused to fade. The first anomaly was age. Based on its motion and chemical behavior, researchers estimate that 3I Atlas may be around 7 billion years old. That places its formation long before the Sun and Earth came into existence. Objects this ancient are rarely observed up close, since most material from that era has been recycled through stars or locked away in distant regions. In practical terms, this means 3i Atlas could carry information from a time when our solar system did not even exist, turning it into a moving record of a forgotten chapter in cosmic history. The second anomaly involved color. Many comets glow green as they approach the sun, and this effect is usually linked to carbon-based molecules, especially a compound known as C2. When sunlight hits these molecules, they emit a green light that telescopes can detect. With 3i Atlas, however, the glow did not match expectations. Data suggested that the comet was low in C2, yet the green color remained visible. This mismatch created confusion because the usual explanation no longer worked. Either an unknown process was producing the glow, or the chemistry of this object was far more unusual than scientists first assumed. The third anomaly came from its metal signature. Spectral readings showed clear signs of nickel being released from the comet, which by itself is not shocking. What raised eyebrows was the absence of iron. In natural space objects, nickel and iron tend to appear together in similar amounts. Here, that balance seemed broken. Some researchers pointed to a compound called nickel tetracarbonyl, a substance known on Earth mainly from industrial processes rather than natural environments. While this idea remains under study, the mere possibility highlighted how unfamiliar the material makeup of 3i Atlas might be. What made these anomalies powerful was not their shock value, but their consistency. Age suggested an origin far older than our planetary system. The green glow hinted at chemistry that did not follow common rules. The metal readings implied processes or environments rarely seen in nature. Each detail pressed against the limits of existing models without clearly breaking them, which left scientists in a cautious but uneasy position. Importantly, researchers avoided jumping to conclusions. Anomalies are not answers, and unusual data does not automatically mean something artificial or threatening. Science advances by testing possibilities, ruling out errors, and waiting for stronger evidence. Still, patterns matter, and the pattern emerging from 3i Atlas demanded attention. At this stage, the comet was no longer just a fast-moving visitor from another star system. It had become a collection of questions wrapped into a single object, forcing experts to rethink how diverse interstellar material might be. The mystery was no longer about whether something seemed odd, but about why so many independent signals pointed in the same strange direction. If these three anomalies truly belong to the same story, then the next step is unavoidable. How far should scientists go when the data hints at possibilities that stretch beyond familiar explanations? As the list of anomalies grew, speculation entered the conversation, because unanswered questions often invite ideas that stretch beyond established explanations. This shift did not come from internet rumors alone, but from comments made by respected voices who openly acknowledged uncertainty. One of the most discussed statements suggested that there was a meaningful chance, estimated at 30 to 40%, that 3i Atlas might not be a purely natural object. That comment acted like a spark. Online discussions quickly filled with theories that pushed far past traditional astronomy, ranging from advanced probes to deliberate technology sent from another civilization. Among the more dramatic ideas was the suggestion that 3i Atlas could be a kind of mothership, moving through the solar system while releasing smaller instruments. In this version of the story, the strange path and unusual chemistry were not accidents, but signs of purpose. A key detail in these theories was the focus on Jupiter. Rather than heading toward Earth, which many would assume to be the main target, some speculated that attention toward the gas giant made more sense. Jupiter is massive, dominates the outer solar system, and is visible from great distances. Because of its size and gravity, it stands out like a marker, which in theory could attract interest from far beyond our star. The region around Jupiter is also relatively stable, making it an ideal place for long-term observation with minimal energy use. These ideas spread quickly because they offered a story that felt intentional rather than random. They connected motion, composition, and location into a single narrative that seemed to explain everything at once. For many observers, the appeal was not fear, but fascination, since the thought of advanced technology passing quietly through our neighborhood is hard to ignore. However, mainstream science remained cautious. Space agencies and research teams emphasize that speculation should not replace evidence. While unusual data deserves careful study, extraordinary claims require strong proof, and that proof has not appeared. From their perspective, the behavior of 3I Atlas can still be explained by natural processes that are not yet fully understood, especially given how little time scientists have had to observe it. This balance between curiosity and restraint defines the moment. On one side, speculation highlights how strange the object appears when viewed through familiar models. On the other, scientific discipline demands patience, repeated measurement, and verification before accepting radical conclusions. Neither side fully dismisses the other, but they operate under very different rules. What matters most is not which theory feels more exciting, but how the conversation itself reflects human nature. When faced with something new, people instinctively search for meaning, patterns, and intention. 3I Atlas has become a mirror for that impulse, revealing how quickly mystery can blur the line between possibility and proof. As the debate continues, one question remains unresolved. If speculation grows strongest when evidence is incomplete, what will happen when future data finally closes the gaps? 3I Atlas is not a danger to Earth, yet it remains one of the most valuable tests modern astronomy has ever faced, because it forced scientists to track, analyze, and respond to something that did not follow familiar rules. For the first time, data from spacecraft orbiting another planet was accepted by the Minor Planet Center, marking a quiet milestone in planetary defense. This visitor showed how prepared we are and how much we still need to learn. If the next interstellar object is less predictable, will we be ready to understand it in time? Share your thoughts in the comments and follow for future updates as new data arrives.